So resuming, in the last lecture we saw that there are instances of fluid flows where it becomes unstable. We saw some examples where comparisons can basically be made. In this particular lecture, we will look into a little of a detail of how these calculations are done. So whatever we did in the water wave calculation of surface gravity wave, expanding that into things like shear flows. So this is at the heart of what is done in hydrodynamic stability, which is known as a modal stability theory. That we are trying to going to understand what normal modes are, that how looking at stability of modes helps, and the basic idea is something that you are already familiar with. So if you think of a pendulum vibration problem, like you have a pendulum of mass m that is suspended from a support using an inextensible string of length L, gravity is what is acting in the problem. If you do a force balance in this calculation about the pendulum, or you can calculate also the moment about the suspending point, you will arrive at an equation for the angular acceleration theta double dot balanced by from the torque you will get, torque by the moment of inertia will be g by L sin theta. Now usually what you do is you do a small angle approximation, and when you do a small angle approximation you can write down your vibration. It obeys an equation which has solutions in terms of sines and cosines, where the oscillation frequency is square root g by L. It's pretty standard. There is nothing that is very new here. What happens when you have two pendulum? Two pendulum which are oscillating, but they are coupled by a spring. So now you can again do the same exercise, and once you work out, you realize that there are two kinds of motion that are there in this problem. One, where the two pendulum exactly have the same amplitude of oscillation, theta 1 equal to theta 2 equal to theta, which means that the spring is completely unstretched. There is no role of the spring. As you can see here, that in this, the equation of motion is identical to the single pendulum. So as if the two pendulum are oscillating exactly as if it's one single piece. In the second case, it's an antisymmetric motion, which means theta 1 is equal to minus theta 2. So they are doing a back and forth motion of this kind. So in this case, when you write it down, you will have a frequency of oscillation that indeed depends on the stiffness. Now why I am highlighting these two motions? Any other motion, any other configuration. So let's say you have an initial condition which looks something like this. This is what I do. I don't disturb the first pendulum, I disturb the second pendulum. This one, initially, I can represent it as a linear combination of the antisymmetric motion plus the symmetric motion, right? If I am saying that initially I give some theta 1 over theta 1, well, this is called theta 2. So theta 2, there is some initial here, and theta 1 initial is equal to 0. So then this one can be theta 1 initial half, this one is minus half theta 2 initial, and here this is plus theta 2 initial, and this one is plus half theta 2 initial. So what you have done, you have superposed that initial condition in terms of the symmetric and the antisymmetric component. And then now you know what is the behavior of each of these vibrating modes. So you can represent the any initial condition as a linear superposition of these vibrating modes. So these are known as normal modes, where the entire structure is vibrating with a single frequency. So in this motion, it is vibrating with a frequency which is square root g by L, and in this motion the entire thing is vibrating with a frequency which is slightly larger than g by L. So any initial condition can be expressed where the structure has these two degrees of freedom, where in each of those degrees of freedom it has a single frequency over which the structure vibrates. That is the idea of normal modes, that you are searching for directions or components or degrees of freedom in which the entire entity oscillates or moves as if it was one single quantity, even though it's not a rigid body. The two pendulum connected by a spring is not a rigid body. So even though here it looks like it's moving as a single rigid body, here there is a relative motion that is there, but the frequency of oscillation is the same for the entire structure that you have. So that is the idea of a normal mode, and this is You have done it for a 2 degree of freedom system. You can take it forward beyond 2 degrees of freedom system. So, 2 degree of freedom system, the next extension is you can take it to more, higher degrees of freedom system, but you can directly jump to a continuous system, a vibrating string. So, if you take a string which is pinned at two ends and you start to find out that how would you understand the motion of that vibrating string, you can superpose all of this in terms of, you will get various kinds of sinusoids. So, these are the fundamental and then the various harmonics that you get in the problem, and each of those would have a corresponding speed of or frequency of vibration that will basically depend on what is the length of the string, the stiffness, the Young's modulus, etc., which will actually give you what would be the vibrating frequency. And there are infinite number of such vibrating modes that are there. The higher the mode, you will get more number of structure in this manner. So, this is it's a system which has infinite degrees of freedom, but it's a one-dimensional system. It's only looking at the deflection is all that you're looking at. Now, you can go to systems which have more than 1 degree of freedom. So, these are plates, and they are going to basically have vibrating modes. So, if you this Khaldini plates, if you look at, there are different shapes. So, you basically try to find out what are the vibrating modes, and when you sprinkle sand on that plate, if you go back to your 1D problem, you can see that there are these distinct nodes that are there in the problem. Nodes would be location where there is zero deflection. So, for the plate vibration problem, when you look at where sand basically gets generated, so the sand is going to actually so what you are doing is you are, by using that bow of a violin, you are trying to excite that plate, and you are trying to excite different modes, and if you do it appropriately, you will get one particular mode that is excited in the problem, and each of those modes will have nodes, and the sand goes and settles on those nodes, because after it is in a node, there is no such motion that will be there. So, you will get very complex patterns, very complex shapes that will start to generate as if the plate was patterned. The plate is not patterned. When you see this kind of a pattern, the plate is perfectly smooth and flat, but the vibrating shape of that plate has these distinct nodes in the 2D scenario, and you can actually visualize this. And obviously, back closer to home, this is more dominant or prevalent in the context of percussion instrument, tabla being one example, where tabla would also have similar vibrating shapes. And if you are not aware, one of the earliest studies of this, of finding the harmonic overtones for the tabla, was actually done by C. V. Raman. And the interesting bit is when you try to find out the ratio between the vibrating frequency. So, for the string problem, the ratio between the vibrating frequency of each of those modes is an integer. When you try to calculate the frequency vibration of each of those sinusoids, the ratio is an integer. Now, for a 2D membrane, it is not an integer. It turns out it will be related to roots of Bessel function. So, when you do all that calculation, you will find it is not an integer. Now, why is that something that we care about? So, the fact is, when you do not have the overtones not related by an integer, that basically creates what is called as dissonance, that each of those modes, they are not related. So, when you are trying to excite all these modes, they are not integrally related. So, it will not come as what we perceive as being harmonious. So, if you just take a plain drum sheet, it will not have that kind of an integral relation. So, the black patch that you have in the middle of a tabla, that helps you tune so that the frequencies have this kind of a close to an integral relation. So, you do not have a sheet of constant thickness, but a sheet which has varying thickness. So, that is basically one way by which you make sure that the fundamental and the higher harmonics have an integral relation, which is why the sound is more harmonic in nature. That's the essence of that calculation. Now, so for fluid flows, the same theory have been applied. The basic idea that you are looking at normal modes, you are looking at that if I have a channel flow, if I have a pipe flow, the problem of Taylor-Kuwait or a solid body rotation, boundary layer, more complicated versions of boundary layer. In all these problems, if I add disturbances, how will those disturbances actually evolve in time? How do we study the evolution of those disturbances? So, the simplest way to start, like we have done a channel flow problem, the channel flow is a flow in the x direction which varies in the y direction. So, what you can now say is that if I add disturbances to this, those disturbances I am basically going to assume that along the flow direction I will consider a Fourier dependence. So, this is again going back to how we did the water wave problem. So, there is no variation in the x direction. So, I am going to assume that there is some kind of a sinusoidal dependent in x along the direction which is the invariant direction and also in time. So, this is a steady problem where the flow does not vary along the direction of motion. If you do this in the pipe flow problem, the flow does not vary along z and theta. In the axial direction, it does not vary. In the azimuthal direction, it does not vary. And there is a temporarily it's steady. So, we basically assume that whatever disturbances I am adding to the system, I will assume a certain Fourier wave or a wave-like form in the system. And the dependence on the radial coordinate is going to be an arbitrary. I mean, I do not know initially what it would be. Boundary layer is a little more complicated because we saw boundary layer flows are varying in x as well as varying in y. So, we can say that if I am doing a steady problem, I will consider a time dependence that is a Fourier kind of a dependence and then some unknown function of x and y initially which we need to work out. In the 3-dimensional problem, if there is no variation in the z direction, you can have a function of x and y and then a Fourier in z and t. So, this is all stemming from the same normal mode approach that we have been looking into. Now, in the boundary layer, what you can always, and this is something which we have done, that variations in y are much larger than variations in x, right. The variations normal to the plate is more rapid than the variations along the flow direction. So, you can make some kind of a wave-like assumption in the flow direction, a loose wave-like assumption in the flow direction. Now, starting point is governing Navier-Stokes. So, you have your Navier-Stokes equation, think of a channel flow problem, you add some noise. So, your premise is that whatever is the base state, velocity and pressure, to that you add a noise in terms of velocity and pressure, and you are assuming that the amplitude of these noise are significantly smaller than your background flow. In the water wave problem, we did this linearization exercise. There was no background velocity there in the problem, but here we have a background velocity. So, exactly in that same manner, we will linearize the equation. We did not have to look into linearization of the equation in water wave problem because it was a Laplace equation. So, we did not have to linearize Laplace equation because it is already linear. What we linearized was the boundary condition. The boundary condition is nonlinear. In the water wave problem, if you remember, the kinematic and the dynamic boundary conditions are nonlinear and we linearize those boundary conditions about the unperturbed location. So, here the boundary conditions are not that complicated, it is just no slip, no penetration. What is nonlinear is we are still dealing with the flow, there is a background flow. So, we are linearizing the differential equation. So, there are different ways by which you can solve it. You can basically solve this exactly, it is a linear differential equation. You can solve it exactly means like you solve it as an initial value problem. You numerically crunch this into a computer, write down a marching in time algorithm, do a finite difference or some spectral in space and solve this as a time and space numerical calculation. You can also use help of Laplace transform to solve this because it is an initial value in time. But what is something that we are highlighting here is we will use the method of normal modes. So, when you use method of normal modes, you say that for a channel flow kind of a problem, the disturbance that you have for velocity and pressure, it can be written as the direction normal to the plate, if I say that is z. So, it depends on z with a Fourier wave in x, y and t. So, there is a dependence. So, and you see there is an exponential of I here that we have added here. It's not that the solutions are going to be imaginary. We are going to finally look at real part of this. So, instead of carrying a sine and a cosine, we are writing it as an exponential because taking derivatives of exponentials are easier rather than taking a sine here and then keeping track. Because if you remember in water wave, we said eta is cos, which means velocity should be sine because of that phase lag. If you were working with an exponential, phase lag is automatic because e to the power minus I omega t, the derivative is minus I e to the power minus I omega t. So, that minus I is automatically capturing the phase difference. So, the algebra becomes easier. That's the short answer of why we are writing an exponential rather than a sine or a cosine. Now, there are steps of, I am not belittling the algebra that is there, but you have an equation here in 3 variables of velocity and pressure, 4 equations. Eliminate the variables, and after elimination you can write these equation in terms of a single variable. That's because you are doing a linear equation, the equations are linear. After all that exercise, you arrive at these differential equations in terms of a single component of velocity and a component of vorticity. So, eta here is actually a component of vorticity that is there. You can use choice of variables that you want in these to actually solve it. This differential equation is what is an equation that tells us we will have to solve for the velocity uz. So, the z component of the velocity subject to the boundary conditions for a given wave number k and a frequency. Now, if I fix the wave number k, so I have fixed let's say I fix the velocity. If you consider it to be a channel flow, it's a parabolic velocity profile. If I fix the wave number k, then the approach is to actually find out what would be the frequency in the problem, because all frequencies would not satisfy the boundary condition. When you solve this differential equation, you will get solutions, but those solutions will not necessarily, all of them will not satisfy the boundary condition. So, you are going to ask for what are the frequencies given a k such that it satisfies the boundary condition. That's the heart of what we have. So, which basically takes us to a dispersion relation. Now, you can also do this by considering viscous effects to be negligible. So, if you take viscous effects are very small in you are doing 2D problem, then you arrive at a second order differential equation which is known as the Rayleigh equation. So, these equations are all linearized version of your Navier-Stokes or Euler's equation. You have taken your governing equation, you have linearized them about a base state, and after a set of algebra you arrive at this equation. So, even though you are thinking these equations are dropping out of thin air, they are a sequence of steps of eliminating variables from your Navier-Stokes and Euler's equation to arrive at it. So, this will come from Navier-Stokes and this will come from your inviscid or Euler's equation. Now, the exercise that we have done, we did exercise of the water wave problem. Now, you can do this for the Rayleigh equation because it is second order. You can do it for different kinds of flow profile. You can do it for a profile like a cuvette, you can do it for a channel, you can do it for discontinuous velocity profiles. You can try for different cases, but we will just see the example that we tried out a while back. 2 liquids of density rho 1 and rho 2, gravity is acting in the picture. Now, what I have done is to have a flow on top. Now, if you remember, this is something which we have touched upon in class couple of times. There is a uniform stream over another stream. The bottom stream I have chosen to be 0 right now. This we have done in what is known as a mixing layer. Now, in class, we chose rho 1 to be the same as rho 2. We didn't look at density effects. So, right now I am keeping density effects, and in the top you are going to solve for this equation. Now, you can see the solution in the top and the solution in the bottom is not difficult because u double dash in the top is 0, u double dash in the bottom is also 0. So, you can solve the problem in the top layer and the bottom layer, and this is the example that I was saying where mixing layers become dominant. This is the meeting of water in Manaus, Brazil, where you can see 2 rivers of very distinct color and they are moving with very distinct speed. They have very distinct temperature and the color obviously comes from the silt content that is there, and the interface is nicely curling up. This
experiment to look at the Kelvin-Helmholtz.
This is an experiment where you have the same configuration where there is a light fluid here over a heavy fluid. So initially there is nothing that is there. Now you gently tilt it. So when you gently tilt it, what will happen is there is going to be a flow. So you first fill it up, and then once you tilt it, you are creating a flow. And very quickly you will see at the interface that the flat interface will curl up. It has now started to curl up. It forms these billows, and if you are in a reference frame of this, you will just start seeing that these billows eventually will start to just mix up. So this you can start off with the same configuration that we have, apply the kinematic boundary condition that we did. So you apply the kinematic boundary condition the top and the bottom, apply the dynamic boundary condition. I'm again summarizing the dynamic boundary condition. So the dynamic boundary condition here includes also surface tension. We did earlier without surface tension, but now you are incorporating surface tension into the calculation. Once you do that, if the two liquids were identical, which is the class problem, in the class the two liquids have same density, no surface tension, you will find that omega has an imaginary part. And as I said, omega imaginary means that there is a growth in the problem. So you have a stream. So this is that mixing layer which you have done as an unsteady calculation, boundary layer calculation. You have done a lot of these. So now you see that that configuration is actually unstable, which means that the interface is going to actually curl up like this. It's going to become unstable. Now, if you were to say that there is no flow, there is only rho 1 and rho 2. This is what we did in the previous lecture. There is a liquid on top of density and a different density in the bottom. Does it remind you of what you have done? We got root of gk in the previous. Here I have given kx to identify that there are two possible wave numbers. So in a 2D problem, there is only one wave number. So in the previous lecture, when we derived in detail, we got root gk. And I told you without any detail that there is a coefficient which is the density contrast. So if it is air sitting on top of water, then rho 2 minus rho 1 by rho 2 by rho plus rho 1 is a positive number. It's close to 1, but it is positive more importantly. But if it is the other way around, which means it's water over air, then rho 2 minus rho 1 is negative, which is why omega becomes imaginary, and it is the Rayleigh-Taylor instability that we saw earlier. So there is never an end to how much you can take this forward, and you can do it also for configurations like this. Does this remind you of something you did recently? This is just a few lectures back, the jet problem. We said that there was a momentum source that was ejected into a quiescent fluid, and we saw that formation of the jet, the secant hyperbolic square kind of a profile using similarity variable, the Beckley jet problem. Now, I said that this interface is a region of very high shear, which is why you have viscous diffusion and the formation of velocity profile like this. Now, when you do a stability calculation, you will find that even for this case, so you had a jet like this, you can perturb the jet like this. This is known as a varicose mode, or you can perturb the jet like this, which is a sinuous mode. And in both cases, you can actually also get instabilities in that problem. So whatever you did in the jet problem in class using boundary layer theory, that also shows an instability. So finally concluding, what about parallel shear flows? I mean, everything that we started discussing, we started with a motivation of that channel flow, boundary layer flow, the flat plate boundary layer flow, but everything that I have shown so far has no direct connection. These are harder problems. These are significantly harder problems to address using stability theory. This is again the original setup that you saw of Reynolds. This is the same experiment done almost 100 years later, the experiment that you see here. So different increasing flow rate. the dye is basically getting more and more disorderly with increasing flow rate. And the same story continues for boundary layer. Flat plate boundary layer. We said Blasier's theory tells us that once you have achieved Blasier's regime, you will have a velocity profile where the boundary layer keeps growing like this, and you will see increasingly smoother, you will have the flat plate boundary layer continuously growing forever. The Rex that we wrote down, which was u infinity x by nu, there is no bound to it. It can keep becoming as large as possible. These are the observations of the boundary layer at different x locations. So, when you go to an x location which corresponds to an Rex that is larger than around 3 10 to the power 5, you see signatures of wavy behavior in the boundary layer. And when you look at the velocity fluctuations, so these are velocity fluctuations at different streamwise location. So, at different points on the streamwise location, you observe that as you keep going further and further downstream, the signal becomes extremely irregular. So, this is something which was done fairly early, which is what is known as the Tollmeing-Schlichting instability or the Tollmeing-Schlichting wave that happens in a boundary layer. So, the flat plate boundary layer that we have learnt in class, we said Navier-Stokes, Prandtl's theory, Blasier's, and nothing else after that. But yes, it is not nothing else. After that, there is an instability that would happen. There is the Tollmeing-Schlichting instability that will happen, which will eventually lead to a turbulent flow. So, you cannot have a laminar flow forever. The laminar boundary layer will not persist forever. So, now if you recall all that you have seen, Dhawan's experiments, you would see that beyond 3 10 to the power 5 Rex, you would have a turbulent asymptote of the skin friction. You cannot get the Blasier's result. It is going to depart from that. So, that happens because the boundary layer stops remaining stable. So, this is what you would get from the normal mode calculation. So, if you do a normal mode calculation, so this is Re based on delta, and this is a non-dimensional frequency. So, this is u infinity square omega by nu square, u infinity square omega by nu. So, it is a measure of the non-dimensional frequency at which you are exciting. So, you excite the boundary layer with a given frequency, you measure, so you see that there is an instability window that is there, that occurs in the problem from the theoretical calculation. Same with the channel flow. So, in the channel flow also you will observe the same aspect, that there is an instability in the Reynolds number wave number plane from the theoretical calculation. The channel flow experimental verifications also have been done in quite some detail, and very nice set of experiments, because these things are not so easy. Any small disturbance that can come from all kind of uncontrolled setting can trigger an instability. So, you have to be very careful how you set these experiments up. So, there is a ribbon here, a vibrating ribbon that is there in this particular setup. So, in a rectangular, so you have to do the calculation is a infinite flat plate channel flow, right. So, you have to have a rectangular cross section of a very large aspect ratio, and you drive fluid through it, and you try to trigger this instability using these vibrating ribbons. So, when you make measurements of what the velocity fluctuations are, this is the longitudinal velocity that you have, and if you make measurements of the velocity fluctuations as a function of distance from the height, so going from the top plate to the bottom plate, the symbols are what you get from experiments at different frequency of oscillation and Reynolds number, and the continuous curve is what you get from theory. And you can measure various other things. You can measure the growth rate of the perturbation amplitude, compare it with theory, and this is going back to that diagram. So, the theory tells us that you have an instability if you are inside this tongue. So, there is a tongue inside which the flow is unstable. When you do experiments, the closed circles are all unstable, the half closed ones are where it is neutral, and these are all stable. So, the experiments give you a some amount of confirmation of what you have already from your theory. This is again the wave number, what you have already been seeing as k. Boundary layer, similar experiments have been done to check what we get, whether you compare the boundary layer profile. You have seen this comparison of boundary layer velocity profile from Nikuradze when we saw in earlier lectures, and this is the disturbance velocity profile measure in the boundary layer. And finally, this is what you would get from comparing experiments with what you get from the numerical calculation of linear stability prediction. So, this is what I thought you should know. This is obviously not the again the complete story, and as I have been repeating, it's not possible to summarize all that complete story is, because whatever I have said here based on that theory, two very simple problems: flow through a pipe and a Couette flow. We have done these in class. Based on all the linear stability calculations we did using normal mode, these two problems are stable. There is no instability. But experiments tells us that there is an instability. We learned that if you do pipe flow calculation beyond a Reynolds number of 2000, the flow stops being laminar. But if you do a normal mode calculation, you will find that it is stable for all Reynolds number. So, this and the Couette flow is stable for all Reynolds number based on your normal modes calculation. So, this has led to an advent of many other methods which have come about, many other questions of whatever assumptions we have made. I will encourage you to, I'll just give some names and you can look into it. So, there is a non-modal stability theory. A very good reference point for this is a book by Schmid and Henningsen. And there is also something which is non-modal, and this is more contemporaneous, non-linear stability theory, which tries to really get into the heart of the question of what is the transition from a laminar to a turbulent state for any of these kind of flows. So, there is an annual review article by Rich Kurzweil, which gives you a nice summary of what is probably the state of art of how we have been looking at these problems. And some of the pictures that I have taken in earlier slides are from again an excellent book by Francois Charroux, which is on hydrodynamic instabilities. So, I am not done justice to what is more recent theory, what is more recent things that we know about it, but if you probably dig deeper into some of these references, you will get an idea of where things are going, where things are, where are we in terms of understanding things. We have made a lot of developments using modal stability theory in understanding a lot of different kinds of problems, but there is a room for going even further, going from asking questions like, how do I transition from a given laminar state to a turbulent state? If you think of that, there are probably multiple states in the turbulent regime. What are the pathways of going there? How do we approach such scenarios? So, it is a combination of using very sophisticated numerical techniques, ideas from dynamical systems. So, there is a whole lot that is there in terms of the future of how you see hydrodynamic instabilities. So, once you go through these, maybe you will find at least some of them interesting enough to pursue further. Okay. So, with that, I conclude.